So now that we've talked about gases and their behavior versus ideal or real, what we're going to look at here is pressure and volume. And we're going to talk about the different variables that affect the behavior of gases. So looking at the first, we're going to look at the relationship of pressure and volume. So looking at these images, I want you to think about what's happening to the volume as you put pressure on a system. So when we look at this, you can see that as I'm putting pressure on a system, you can see that your volume is going to be indirectly related. So how we're going to write that is that as you increase your pressure, you're going to have a decrease in volume, and vice versa to that. So as you decrease your pressure on a system, you're going to increase your volume. This allows particles to move around more and sometimes even expand or put pressure on the exterior of the system. How we're going to relate this mathematically is by Boyle's law. Boyle's law is defined as P1, V1, and 1 standing for your initial conditions, equals P2, V2, which stands for your final conditions. How does this look graphically? Well, for math class, you should think about how we graph an indirect relationship. Based off an indirect relationship, as one goes up, the other one goes down. It causes this nice curvature. On the independent axis, we'll put the volume, and on the dependent, we'll put the pressure. These could be interchanged. The next variables that we're going to look at is temperature and volume. So how does temperature and volume relate? Well, as we heat something up, we know that we're going to be adding more kinetic energy into the system. As we put more kinetic energy in the system, these particles are going to spread out. As they spread out, we define this as volume. So we know that as we increase our temperature, we're also going to increase our volume. And the opposite of that is as we decrease our temperature, take out average kinetic energy, we're going to decrease our volume. Graphically, we know this is a direct relationship, which is shown as follows. As I increase my temperature, we know that volume as well increases. Mathematical representation we have for this is called Charles' law. Charles' law shows that V1 over T1, so your initial settings, equals V2 over T2, your final settings. Now you can calculate based off from an ideal gas. The last set of variables we have is between that of temperature and pressure. So I want you to think if it's this a fixed container, so the sides of the walls can't move, what happens as the temperature increases? It doesn't have to be a fixed container because pressure, remember, is the force exerted by a particle on the surface of the container. So in this case, as I increase my temperature, you can see that the magnitude or the thickness of this arrow is getting larger. So as I increase my temperature, I'm also increasing my pressure. But as I decrease my temperature, I'm also decreasing my pressure. Again, remember temperature is average kinetic energy. So as the particles have more average kinetic energy, they're moving around faster. As they move around faster, they run into the container with more force. How we define this mathematically is through the Gay-Lussac's Antoine formula, which is P1 over T1 equals P2 over T2. Graphical representation of a direct relationship is shown with a linear line. We know temperature on the independent axis with pressure on the dependent. Again, these can be flipped depending on which variable you're manipulating. So why are these all important? Well, when we look at this, we are going to combine all of these laws together into what we know as the combined gas law. This is found on table T of your reference table. And one of the big notes here is that temperature must be in Kelvin. In order for this relationship to work, these must all be in Kelvin. So let's look at some practice problems. When we're looking at practice problems, one of the things that we need to do is identify which variables we're actually using and what they actually stand for. So some of these are a little bit familiar to us and some of them are not. In our first one, we're looking at a gas at 608 millimeters Hg. Well, this is our pressure. So our P1 is held in a container with a volume of 545 centimeters cubed, which we know is our volume one. The volume of the container is increased, so there's our V2, and we want to know the new pressure. So we're looking for P2. Again, using the combined gas law, P1 V1 over T1 equals P2 V2 over T2. We know temperature is not changing, so this is being called a constant. We can just eliminate that. So which formula are we going to use? P1 V1 equals P2 V2. Now plug in the variables in which you already know. P1 we know is 608 millimeters of Hg. Our volume we know is 545 centimeters cubed. As long as our units are staying constant, which they are, we don't need to write them. P2, and now we have V2, which is 1065 centimeters cubed, and we solve for our unknown. As you calculate this, we need to divide the right side by 1065, divide the left side by 1065, and you should end up with a P2 value of 311.14 millimeters Hg. Looking at sig figs, we have 3 sig figs as our least amount. So we round this to 311 millimeters of mercury. Looking at our next sample problem, what will be the volume of a gas sample at 335 Kelvin if its temperature at 273 Kelvin, or sorry, if its volume at 273 Kelvin is 8.57. So what I always tell you to do is identify what you're looking for. So we're looking for a volume change, so V2. We know our initial V1. And our initial V1 is going to be our 8.57. Oops. And we know that our T1 is 273K. So looking at this, we have V1 over T1 equals V2 over T2 because pressure is being held constant. So looking at our V1, we know is 8.57 liters over our temperature, which is 273 Kelvin, already in Kelvin, so we don't need to convert that. We're looking for our new volume over 335. So you're going to cross multiply this, leaving you with 273x divided by 273, giving you an answer of 10.52 liters. Sig figs, least number of sig figs is 3, so your answer should be 10.5. Looking at our last practice problem here, we have a sample of oxygen gas has a volume of 205 centimeters cubed. When its temperature is 22 degrees Celsius and its pressure is 30.8 kilopascal, what volume will the gas be at STP? STP stands for standard temperature and pressure. You can find these values on table A. One of the things that we need to do is for our temperature, we need to convert that. So 273 plus that of 22 gives us 295. So we know our B1, we know our T1, we know our P1, and now we're going to look for our P2, V2, and T2. Well, the nice part about this is we're looking for our volume, STP, in kilopascals. We know STP is 101.3 kilopascals. We know the temperature is 273 Kelvin. So now that we have all our units the same, we know that we're going to have 205 times our pressure, which is 30.8, over our temperature, which is 295, equals our STP of 101.3 multiplied by X over 273. Again, you're going to cross multiply these, solve for X, in which you should end up with X equaling 57.68. Sig figs here is 3 sig figs. 3 sig figs would leave you with an answer of 57.7, and your volume in this case is going to be in centimeters cubed. Some other laws that are important to think about when we're dealing with gases is what's called Avogadro's law. Avogadro's law is gases with the same volume, at the same temperature and pressure, have the same number of particles. It does not matter the identity of the gas, but that the gas itself in the count of the particles. So you can see helium, hydrogen, or even that of methane all have the same amount of particles, as long as you have the same volume, same temperature, and same pressure. So now what I want you to do is practice some Regents questions.